All right, up and running here. And going to talk a little bit about a thought process that's going to start out, I think, with something that's pretty easy to follow. Going to build towards more difficult procedures. And hopefully with that thought process, they won't be more difficult procedures. And try to make some connections with what we've been practicing all semester. And so I hope you watch it from start to finish, because like Bolero, I think it's going to build. All right, so let's have at it. Let me get a good marker here. Yep, that'll do. All right. All right, so I'm going to call this conceptual elimination exercise, a conceptual elimination exercise. Now, as many of you know, I have a lot of different opinions about mathematics. And one of them is what you're taught, excuse me, in Algebra 1 seems to be passed down through the ages, that you subtract 3 from both sides and you get x equals 2. All well and good. I don't think it serves you well going forward. I don't think it helps you to develop an ability to think mathematically as quickly and clearly as one needs to or would want to. So why do I feel that way? Well, please pardon my dear Aunt Sally doesn't have a whole lot to do with logs and exponents and sinusoids and integration and differentiation, and who knows what's beyond that, because I only teach a certain level of high school math. So 2 plus 3 equals 5. We can say that we understand that, see that. So 2 equals 5 minus 3. It's a slight, subtle change in approach, but one that I think leads to an ability to think mathematically more easily. Addition of 3 becomes subtraction of 3. So it's operational change associated with the number that's with that operation. I think we can see that 2 times 5 equals 10, and 5 is equal to 10 divided by 2. Multiplication becomes division. Very subtle change. 5 squared equals 25. 5 equals square root of 25. Some inverse operations here. And 2 equals log base 5 of 25. Something written in exponential form could be written in log form. Very useful. So on and so forth. So let's look at a couple of situations that continue to baffle people and see if we can put that bafflement to rest. So oftentimes Algebra 2 and pre-calculus students will expand. Let's make this one a 4. Let's make this one a 2. Let's square it. Let's set it to 0. All right, a lot of times people will expand that, kind of put it into a ax squared plus bx plus c form and take something that's fairly straightforward, make it more complicated. Not the way to go. Always try to simplify, I think. No. If something equals 0, let me see, what does, I said a different approach. I guess that has to equal 0. Well, there are some things standing in the way from getting us to 0. What's standing in the way? Subtraction of 2. I think addition of 2 gets rid of that. Multiplication by 4. I think division by 4 gets rid of that. I think squaring, plus minus square rooting. I don't know how many of you see plus minus the square root of a half. And in class, we said that's the same thing as the square root of 2 over 2. Just mentioning. All right, square root of a half, 0.7, right? 0.7 squared, 0.49 gets us pretty close to a half. And we've been approximating this to be 0.71, gets you even closer to a half. Anyway, back to the original topic. We've taken care of that, we've taken care of that, we've taken care of that. Minus 3, I think positive 3. And I think if you replace this letter with that, you'll actually see that that left side becomes 0. So, series of inverse operations. So, on the test, folks had 4x squared minus 20 equals 0, I think, something like that on the last test. A lot of you missed it. Well, you can't afford to at this level of math. So what do we have? Addition of 20, division by 4, plus minus square root, we'll get the square root of 5. And if this had been a positive, then that would be a negative, and you would have pulled an I out. Right? It's just a question of grammar, how we express that. That's how we express it. And I hope you see that if you square I, you get a sign change, which is going to get rid of positive 20 when all is said and done. Okay, so that's what we're looking at. Now we extend it to the other functions, which means you need to know the inverse operations of logarithms, of exponentials, of sinusoids, so on and so forth, of e to the x, and the inverse of ln of x. Those are the inverses. And you're trying to get familiar with those. So let's take a look at those. And then we're going to extrapolate with what we're working here. We're going to generalize a little bit, see where it takes us, especially in terms of graphing, because we're getting to the end of the semester and I'm expecting folks to be able to solve or approximate via graphical picturing. Okay, so let's see, what can I ask you? Well, here's a typical question here. 2 log base 3 of x minus 5 plus 7 equals, let's see, how about we get 4 is 11. And if we want to put it into the situation we've been talking about, we could. Now, obviously, if you know how to solve that already, you go, keep doing what you're doing. But for folks who are struggling, you might want to consider this minus 4 equals 0 and get us back to the original discussion. We got to get rid of some things, right? Maybe yeah, we'll keep it like this. So I think you got to get rid of subtraction. I think you got to get rid of multiplication. You need to know the inverse of log base 3, which is 3 to the. And then subtraction of 5, addition of 5, and we get ourselves a number. 3 squared is 9, plus 15, plus 5 is 14. All right, so let's put 14 minus 5 in here. Oh, that's 9. Oh, what do you put on top of 3 to get a 9? 2. 2 times 2 is 4, minus 4 is 0. Okay. So the ability to do that is pretty straightforward. We're going to generalize it soon. And yes, you need to know that the inverse of 3 to the x is log base 3 of x. Simple enough. We could have looked at something like e to the x divided by 3. Let's see what we can get here. Plus 2/3 equals 1. So what could we do with this? Well, we could certainly e to the x over 3 equals minus 1/3 equals 0. So how do we deal with this? Well, subtraction of 1/3 becomes addition of 1/3. Looks like we got multiplication by 3. Multiplication by 3. And then we got the inverse of e to the x, which is ln. Well, 3 times 1/3 is 1. What's the ln of 1? We've been working on that. That's 0. I'm sorry. 3 times 1. What did I do? 1/3 division by multiplication by 3, 1. ln of, oh yeah, I'm sorry. Plugging it in here, right? So the ln of 1 is 0. E to the 0 is 1. Early in the morning here, 1/3 minus 1/3 is 0. So the brain slowed down a little bit. I'm getting old. All right. So what's going on? What's going on with functions? Let's say we have, 2x to the 7th minus 3, and we want the inverse. We want the inverse. Well, you can think of this equal to 0. Start with the letter x. And ask yourself, what do we have to get rid of? Subtraction of 3, addition of 3, multiplication, division. What undoes x to the 7th? The 7th root. And we're using the same thought process to write an inverse. Shouldn't take long. Shouldn't take a lot of writing. Should take some processing. All right. How do you check to make sure you don't make a careless error? Yeah, put a number in. I guess 2 is the friendliest number here. 2 to the 7, 2 to the 6 is 64. So 128 times 2, 256 minus 3 is 253. So I started with a 2 and I got a 253. So down here, I'm going to start with a 253 and see if I get a 2. If I made a careless mistake, I can go back and I can fix it. I'm going to go to graphic in a moment. So 253 plus 3 is 256. The 7 through 256 is 2. It checks. All right. So what have we been doing? We've basically been taking a major operation, which we call f of x. We've been multiplying it, and we've been adding a constant, and we've been setting it to 0. That's basically what we've been doing so far. We're going to take it one more step in a moment. All right. So what do we have? How do we solve this? Well, you got to get rid of the addition of C. You got to get rid of the multiplication with division, and you got to do the inverse. That's it. That's what we're doing every time. 90% of the equations we solve. The only ones that are really slippery are, something like this, quadratics. Do we need to factor it to make it easier solution? Do we need to put it in graphing form so we can do this process? Quadratic formula, which I don't use anymore. Or can we just look at it and know enough about the inverse operations to tell you what the answer is? All right, so there's a variety of skills you're trying to put in your pocket, and that's what you're working on now. Now, how do these get more complicated? Well, we could play with the argument, and the argument could become not just x, but x minus a over b plus c. So how would we solve that one? And we'll do a couple of that look like that were on the test. And we'll see if we can make some gains. Well, I think you got to get rid of that. I think you got to get rid of that. I think you got to get rid of the major operation. I think you got to multiply by b. And I think you got to add a. And I think we found ourselves a solution. Yeah, the argument's a little more complicated, but it comes back to addition and multiplication in this context. That's very helpful. Why is it very helpful? Because if we can make this number 0, we always get that. And if we can make this number 1, we always get b plus a. And that's going to be very helpful in our graphing. But let's solve an equation first that fits this mold. What did you have? You had something like 2 times the log of base 3 x minus 4 over 5 plus 6 equals 7, something like that. I don't know. 2 plus 6 is 8. So let's make it equal to 8, right? Because this is going to get us a nice simple solution. And we just want to see it. All right, so what are we going to do? Well, if you already know how to solve this, keep doing it the way you're doing it. But this concept of 0 equaling 0 might just move the dial a little bit for some of you. That's why I'm doing it. So we're going to subtract 8 and make this minus 2, and we'll set it to 0. Okay, so what are you going to do? Well, you got to get rid of that. You got to get rid of that. You got to get rid of log base 3, which is 3 to the. You got to multiply times 5, and you got to add 4. All right, so let's go back to the original question. I forget what it was. Oh my God, I forgot. Plus 6 equals 8, I think. Yeah, I think that's what it was. God, I hope so. Well, let's check it out. 3 times 5, 15, plus 4, 19. 19 minus 4, 15 divided by 5 is 3. Well, I think I set it to 10, right? Well, that's 1. No, that's 8. Okay, so that's what it was. Losing track of where I was. Thought process. So how's it helpful? Well, it's helpful in graphing. Again, if we want to graph something like y equals 2 log base 3 of x minus 4 over 5 plus 6. Okay, I would love to make it 2 times 0 plus 6. And I'd love to make it 2 times 1 plus 6. Those are 2 points. And yes, you do have to learn that logarithms have domain restrictions, that numbers have to be bigger than 4 in this parentheses, or the calculation can't be done. And we've talked about that in class. It doesn't mean you've heard it yet. Based on the last test, Doesn't seem like you have. Okay, most folks still didn't draw that, and we got 3 weeks left in the term, and it's coming your way again on Friday. All right, so what are logs? They're exponents. How do we use exponents? Growth and decay, right? What does growth and decay mean? That at a particular time, something's growing like the grass out there, or something's decaying like the compost. I don't know if that's true or not in terms of an exponential model, but just saying quantities grow, quantities decay. If you don't have a quantity here, well, then how are we going to talk about at what time that quantity exists? All right, so that parentheses got to be positive, which means x's have to be bigger than, that means that x minus 4 over 5 has to be greater than 0. X has to be bigger than 4. All right, so what do we know about logs? Well, we want to make a 0. Well, log base 3 of 1 makes that happen. We want it to equal 1. Well, log base 3 of 3 makes that 1. That's what you're trying to see. All right, so and then we said it equals 8. Well, 8's a graph. Let's say that's 8, y equals 8. All right, that's that graph. All right, and now we're going to graph this. So we're going to make this thing 1. So 5 times 1 is 5, plus 4 is 9. So 9 gets us a 1. And 9 gets us 8. Because 1 times 2 is 2, plus 6 is 8. So 9 gets us an 8 on this side of the equal sign. Well, we want to make a 3. All right, well, 5 times 3 is 15, plus 4 is 19. So up here somewhere, 19. I got a scale, that's 5. It should be further out. But for the sake of 5, I'll move it further out. Okay, 19. All right, so what do we get when we put a 19 in? We get this. What's that? That's 1. 2 times 1 is 2, plus 6 is 8. Oh, boy, did I butcher this one. All right, I don't want to make a new video, so excuse me. I'm tired talking to you. So if I put a 9 in, you probably saw it. 0 times 2 should have been 6. But that's why we do this, to check for errors. And I just made one. We all do at different times. I just made one, a big one. All right, how many times have I told you? Log base 3 of 1 is 0, and then I didn't do it myself. I'm just chatting and I'm tired. All right, so but at least I found it. So 9 gets you 6, which is below 8. Probably there. 19 gets you 8. And so what's our graph look like? Talked about the asymptotic behavior. All right, and that's what the graph looks like. So what are we doing? We're taking a function with respect to some values, and we're trying to make it 0, and we're trying to make it 1 when this becomes 0, not the parentheses, the whole thing, f is 0. All right, when f of whatever number in here creates a 0. 2 times 0 will always get us that. Whatever number in this function makes a 1. 2 times 1 plus 6 gets us that. All right, so I don't know, losing my train of thought here, but I'm still going to post this because I want you to think about it. Let's do one more. I'll try not to talk so much and just do it. So what do we have? We have something like 4 e to the x minus 3 plus 5 is equal to, let's see, 13. So I'm going to do the graphical first. Y equals 5 is the asymptote. We have exponential growth. I definitely want to put a 3 in. My first jump is 4. So that means I'm going to do a 9. We said standardize it. Make a jump of 3 times that, 12. How do I make that the number 3? 4.1 minus 3, 1.1. E to the 1.1 is approximately 3. There's your 12 plus 5. There's your 17. And that's 4.1. Right? And I want a height of 13. Well, height of 13 is between 9 and 17. I better get an x between 3 and 4.1. All right, now we solve it the old-fashioned way. 8, 2, ln of 2 plus 3. What's the ln of 2? 0.7-ish. Rule of the bankers use. 0.7 plus 3. Does it look like 3.7 is bigger than 3, but less than 4.1 for a height of 8. That's what we're going to be practicing. Okay, so 90% of equations fall into this thought process. We want to get good at it. We want to make sure we know the inverse of e to the x is the ln function. And the inverse of the ln function is e to the function. We want to know that the inverse of 5 to the x is log base 5 of x and vice versa. We want to know that the inverse of sine is arc sine, so on and so forth. Obviously, there's a lot of memorization to the restrictions on arc sine and arc cosine. That's what you're studying. That's what you're trying to prove to me, you know. All right, so I hope that video may help someone. Sorry for a couple of the careless errors there. Hopefully you saw them as I was making them. That would be great. Okay. Ciao.